Hi, hello, this is Abid again, and in this lecture, I'm going to discuss all about the principal values and principal direction of a real symmetric tensor. So, let's write down here something principal values. Oh, so bad. I'm going to so, yeah. Principal, principal values and principal directions. Principal directions of real real symmetric tensor. Symmetric and real symmetric tensor. Okay. So in this lecture, the lecture is all about how to find out the principal reaction or principal values of a real symmetric tensor. So you have to understand the symmetric tensor and the real symmetric tensor. So what is symmetric tensor? We know its tensor is said to be symmetric. Say for example, T is said to be symmetric. Is it equal to its transpose? Right? Transpose. You say we have already learned from the previous lectures that. Then what are the real symmetric tensor or real tensor? Real tensors are nothing. Real tensors are those tensors that we usually use in your real life. Say for example here, stress tensor, stress tensor, stress tensor, or it might be a strain tensor, or it might be a rate of deformation tensor. Any kind of tensor that we use in real life, and that must be a symmetric tensor. So, rate of deformation, rate of deformation tensor. So, these tensors are symmetric, right? So, what is the symmetric tensor? You know that a symmetric tensor TA, T plus is transpose T divided by 2, right? If I'm not wrong, I'm not sure about that. Yeah, it is. So these are symmetric. So we would find out that we would find out that for a real symmetric tensor there always exist at least three eigenvectors which we shall call the principal direction. So there will exist three eigenvectors which we will call the three symmetric. Corresponding eigenvalues called the principal values. So we would prove that in a space for we find three principal direction we would find three principal direction will get for three dimensional and two principal direction will get for two dimensional. So I'm going to give you an example for two dimensional because three dimensional is so complicated. If you understand the two dimensional, then definitely it would be better for you to understand the three dimensional. So we first go to the two dimensional example or something like that. Say for example, uh, T is a tensor, right? Say I'm going to change the color here. I'm going to use different color. So for example, T is a tensor, right? And N1, N2 is two eigenvectors for two-dimensional case. N1 and N2 is the eigenvectors, right? And the alpha 1 and alpha 2 are the two eigenvalues. So you can write down, so from the eigenvalue and eigenvectors definition, so you can write down here T N01 equal to alpha 1 N1, right? So for example, this is equation number 1, and we have another equation. So N2 equal to alpha 2 and N2, right? So you can write down that. So you can say this equation number 2. Now if we multiply this with N2, then we will get um, N2, right, dot N1 equal to alpha 1 N1 dot N2, right? And if we multiply this with N1, then we will find uh, N1 dot N2 equal to alpha 2 N2 dot N1. Or we can write down here alpha 2 N1 dot N2. So it doesn't matter for corresponding or it doesn't matter in cross product, right? So it's the same as this N2 or N1, right? So from these equations, and we know that uh, A tensor should be symmetric when, uh, say for example, T should be symmetric when it is equal to its transpose, say T. transpose, right? That means you can write down. That means you can write down here n1 dot, say here, this sorry, this should be n1, right? Yeah, n1 dot en2 equal to, so we can write down this n1 dot n2. So we can write down n2 or n1, doesn't matter, dot t transpose n1, right? And if this t transpose is same, then we can write down here n2 dot tn1, because you said it's a symmetric tensor. That was, you say n2 dot t, n2 dot tn1 equal to n2 t transpose or something like that, t. So this and this same, right? So n1 something. So we can here we can, so we can write down, say here, so n2 dot tn1 equal to this. So n2 dot tn1, so you can now write down n2 dot tn1 equal to n1 dot tn2. So this should be equal, right, at this moment. So because from transpose of t, we can write down that. So we can write down here n1 dot tn2, right? So from there, if we replace the value of that, so value of that here, it is that. I'm going to change the color. Yeah. So what is the value? What is the equal of that? This is the equal of that, right? Yep. So we can write down here um, alpha 1 n1 dot n2 equal to, and the corresponding value of that is alpha 2 n1 dot n2, right? Yes. So we can now write here alpha 1 n1 dot n2 minus alpha 2 n1 dot n2 is equal to 0. So we can write down alpha 1 minus alpha 2 times n1 dot n2 equal to 0, right? So if it is real symmetry vector, then this shouldn't be 0, right? So then definitely this should be 0. So if it is 0, so n1 dot n2 equal to 0, so we can write down that. So uh, from the dot product definition, we know that n1 dot n2 equal to norm, that means length of n1, times norm, that means length of n2, equal to cos theta, and theta is angle between them. So this must be 0 if theta is 90 degree. So if theta is 90 degrees, then cos 90 degree is 0. So 0 times this is equal to 0. So if the angle between the n1 and n2 is only 90 degree, then definitely n1 dot n2 is 0. Then that means uh, if that means, what is say, that for a real symmetric tensor, there so we imagine that T is a real symmetric tensor, right? So for real symmetric tensor, there always exist at least three eigenvectors if it is in three-dimensional case. And we have seen that it's two-dimensional cases, two eigenvectors here that are mutually perpendicular to at least two. So there are a lot of eigenvectors, right? So we know there are a lot of eigenvectors of a tensor. So we would find at least three for three-dimensional and two for two which are perpendicular to each other, right? So I hope you've got the analysis. Say again, say T is a tensor. So T tensor has a infinite numbers of eigenvectors, right? So it is three-dimensional, then we would get at least three eigenvectors, say n1, n2, and n3 which are mutually perpendicular to each other. And if it is two-dimensional, then we'll get n1, n2 which are mutually perpendicular to each other, right? Yeah, so that's the main theme of this lecture. So I hope you have all um, get this lectures and what I have tried to make you understand that. Thank you very much for being with us, and I'm going to see you on the next lecture.